Hello everyone, welcome to the nice seminar. Today we have John Chaika, who will tell us about mildly mixing rank 1 transformation with no self-joinings, minimal self-join.
That does not have minimal self-join. Okay, yeah. So I want to thank the organizers for the opportunity to give this talk. I'm very excited to give it here. It's always a great pleasure. I really like this seminar that I've been lucky to participate in this year. So I want to start off by saying that this is a talk in abstract ergodic theory. I know a lot of people in the audience don't really spend all of their time doing it. In fact, I don't spend all of my time doing abstract ergodic theory anyways. So please feel free to ask questions, slow me down, all of those things.
Hey, why is that interesting?
I'll get to that. That requires, I think, a little bit of build up. Hopefully I'll convince you. That was something I wanted to do in the talk. And the main purpose of the talk is this is the main theorem of the talk, that there exists a mildly mixing rank 1 transformation that does not have minimal self-joinings. So I've underlined 3 different terms. I don't expect anyone to know what they mean currently other than me. So I'll first start off defining these, and I should mention that this answers a question of Thouvenot. Okay. All right, so let's get started with the first definition, which is adjoining. So definition. And maybe actually I'll use this board. So definition. Let equal to x b. I'll usually press 4L sigma algebras in this talk, but for the very first definition, I'll leave them in. So x, b, mu, comma, t, and y equal y equal this b sub x, b sub y, comma nu, comma s, b2 ergodic probability measure preserving systems. Adjoining. Joining of x and y is a measure sigma on x cross y, so that it has 2 properties. One is the projections onto x of sigma is equal to mu, and the projection onto y of sigma is equal to nu. So if I look at an x measurable set and cross it with y, the measure that sigma will give it is the same as the new measure of that set, and similarly for the other coordinate. And the second condition is that I want it to be t cross s invariant. So if I just have condition 1 and I ignore this condition, that's called a coupling. So these are called sort of dynamical couplings. And so let's do some examples of joinings. So mu tensor nu is always adjoining. So mu tensor nu is always adjoining. And the finite measure setting, which is what the vast majority of today's talk is about. Now, what happens when x equals y? So if my 2 measure preserving systems are actually the same, I'm guaranteed to have other joinings. So I definitely get some more joinings. Get more. So for example, we could look at, I could have the map that sends x to x cross x. X comma x, and this map pushes forward mu to give me a joining on the diagonal. Right? Gives a joining on the diagonal. And T cross T acts on this and is isomorphic as a measure preserving system to just the action of X. Now I can be much fancier than this, and I could have my map go to t to the k of x. Right? And so this is maybe quote on the diagonal, so it's a shifted diagonal, and I might as well create some notation for this. This notation will show up a little bit in this talk. This will be delta of k. I'll just use that as the notation. Okay. So let's do another definition. If the only self-joinings, the only ergodic self-joinings of x. So what do
T needn't be invertible.
what?
These don't have to be invertible.
All of today's talk is about invertible systems. Thanks, Steve. Any other questions? Okay, if the only ergodic self-joinings of x are the product system, because I want to allow weakly mixing systems to be to have minimal self-joinings, and delta of k for k and z, we say x has minimal self-joinings. Which I'll abbreviate as MSJ. Everybody happy about this? So this is maybe suggestive terminology. It's essentially the smallest number of ergodic joinings you could hope to have, so long as you want to stay in a realm that allows you to be weakly mixing. So that means you want to allow the product measure to have to be an ergodic self-joining. So hopefully this is suggestive terminology. And let's make a couple of remarks about minimal self-joining, a couple more remarks about joinings. So one can ask, why do we care about joinings? Going back to Peter's question
That we care about. You're going to explain all three conditions.
Not everybody here cares about it yet. And maybe I want more people to care about it than cared beforehand. So let me give you two reasons why maybe you should care about this. And reason one is factor. So reason one is factors. There. Factors. Okay, so factor maps of measure preserving systems give you self-joinings. So if y is a factor map of x, we'll do it like this, x, and I've got factor map y, and I've got some kind of projection map here. So what does it mean to be a factor map in dynamical systems? So I have my map T that sends me from the upstairs space. I have my map y on the downstairs space, and I've got the map S here, and I want this diagram to commute. That's what it means to be a factor in measure preserving systems. And I automatically get a joining on x cross x from this factor. Indeed, I have a disintegration map. From disintegration of measures, I can disintegrate my measure mu over this and have a family measure of measures on x that are supported on the fibers of this map pi. And what I can do is I can just take the integral of sort of the following measure. So I take the same fiber and I take the product of that fiber with itself, not with any other fibers, just with itself. And I can then integrate with respect to the downstairs measure. So this is d nu of y, and this is a joining, a self-joining of x. So you could imagine, I think it's a fairly natural question in math to understand the factors of the objects you're concerned with. So if you care about that in dynamical systems, one of your tools you could try and do is to understand the joinings of this system and use that in turn to understand factors. Let me just make a remark that the joinings I'll talk about today do not come from factors. So not every joining comes from factors, but plenty of them do. And if you can prove some rigidity results about joinings, show that they're restricted in some ways, you have a good chance of showing restrictions on factors. Okay, so that's one more reason. And then there'll be another reason, which goes back to an old question of Rocklin's question. Okay, and what's Rocklin's question? So Rocklin's question is if X is mixing, and I'll define this in a moment, is it mixing of all orders? Of all orders. That is, if for all A, comma B measurable, the limit as n goes to infinity of the measure of A intersect t to the n of B is equal to the measure of A measure of B is the limit is for all A1 comma out to AK, N1 comma out to NK minus 1 going to infinity, the limit as I need to ups. Sorry about this notation. It probably could be better notation. The limit as I goes to infinity of the measure of A1 intersect T to the N1 upper I, A2 intersect intersect T to the summation of my N upper I sub L's of A sub K equal to the product of the measures. Let me say what this means in words. Okay, so what I could do, so this condition up here is called mixing. So what I'm doing is I'm taking two sets, I'm moving one forward by the dynamics, and I'm leaving one staying put. And what I want is that asymptotically, they're converging to the product measure. So where I start and where I am after a long amount of time is asymptotically independent. That's what you should say about this. But what if I know where I'm at one time and then at a second time and at a third time and so forth, and those times are stretching apart further and further. So I want to consider the sums of these times, and I want all of those to become independent. Does this imply this? And in general, for processes, this is not always the case, but we don't know of a counterexample to this right now.
That's assumed to be false.
I don't know.
So we don't have counter. I mean, are you throwing some belief?
No, I don't intend to throw any belief. Okay, I don't. Maybe other people have beliefs. I don't. Okay. Yeah. I mean,
Most people try to create a counterexample, and eventually it's sort of discouraging.
maybe that's the right thing. There's also some, there's also some candidates you could imagine trying to build for counterexamples that have been proven to not, there's no counterexample that looks like that has been shown. So I don't know. So I didn't mean it to come across as I have an opinion on it, because I do not. Other questions? Okay, so what does this have to do with joinings? So what you could imagine doing is let's just do the threefold case. What you could imagine doing is I could imagine sending my map X to a map X, comma, T to the N of X, T to the N plus M of X. Plus N of X. Okay, and maybe I want to do this along a subsequence. Okay. And if I'm two mixing, so long as Ni and Mi are going to plus infinity, the projections of this joining will be the product measure. Okay? But if I'm not threefold mixing, then there'll be such an example that's not the product measure on all three factors. So you could imagine attacking this problem by studying the situation where you have a joining that is pairwise independent. So if you project onto any two of the coordinates, you get the product measure, but it's not the product joining, or to prove that such things can't exist. Okay. So hopefully this motivates a little bit why on earth somebody would want to care about it.
Okay, but this is still something you could create, right?
So you can, yeah, so Alon's asking a really good question here. So if you take the shift on two symbols and the product measure on that, you can build joinings like this. However, there is not known of a weakly mixing example in entropy 0. And it is known that if you have a 2 mixing systems that's not 3 mixing, you would have to have such a example. So asking this question in weak mixing entropy 0 is an open question. And if you show none can exist, you've resolved Rockland's question in the negative. Did that address your question a little bit? Okay. Any other questions? Okay. Thanks for those questions. Really great questions. Please keep questions coming. Okay, so that's the part. Hopefully at this point, I have defined joinings, self-joinings, and minimal self-joinings. People happy about that? And maybe said a little bit of why somebody should care. But let's keep going with this. So let's next define what it means to be mildly mixing. So definition. X is mildly mixing if it has no rigid factors, there's no rigid functions. That is, if there exists F in L2 and N1 comma dot 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 going to infinity, so that F imposed with T to the Ni converges, say, in L2 topology to F, then F is constant. And I wrote this definition wrong. I should have written the word non-trivial. Okay, so you're called a rigid function if you have this property. Okay, the constant functions are always rigid functions, so we call them the trivial rigid functions, and you're mildly mixing if you have no non-trivial rigid functions. Everybody happy about this?
What's going to do the spectrum?
I'm not 100% sure, but let me say some of the things that are connected to this. Okay. So this is equivalent to well, you could have a closely related property, which is that for all A with the measure of A strictly between 1 and 0. Okay, we have that the infimum of n greater than 0 of the measure of A symmetric difference of T to the n of A is greater than 0. So a set never comes back almost entirely to itself. This is equivalent. There's a second version, which is for all y, comma nu, comma s, a conservative, possibly infinite measure preserving system. Infinite measure preserving. Ergodic system. S cross T, T cross S is mu tensor nu ergodic. Okay. So let's take a moment to discuss this. So I want to be in the context where I allow infinite measure preserving systems, because I already know before I knew the definition of mild mixing when any ergodic finite probability measure preserving system crossed my system was ergodic. That's an equivalent condition for being weak mixing. But I want to allow my ergodic systems to become more general. And so I want to ask what conditions work for that. And it turns out it's exactly equivalent to being mildly mixing. And I want to request my systems are conservative, which means that that for any set of positive measure, almost every point in it returns infinitely often. So infinite measure preserving systems for which the Poincare recurrence theorem holds. You can, of course, ask which ones it doesn't hold for. And the ergodic ones are shift on the integers. They're isomorphic to shift on the integers. So there's at least one. There is one. It's a nice one, but yeah, I don't want to consider that one. Is everybody happy about this? And so I think it's natural to compare this condition to being mildly mixing. Now, of course, I'm using this word mixing, so I think I should justify why we're using the word mixing for this. Oh, I should give credit at least to this one. This is Katz-Nelson. No, this is Furstenberg and, sorry. I think it's Furstenberg and Weiss. Let me check my notes. It's from the paper that introduces mild mixing. I think it's Furstenberg and Weiss in the 70s. Yeah, Furstenberg and Weiss. Okay. This is Furstenberg and Weiss. And so now let's state this theorem, this third version is a little bit more technical to state, but it's the one that involves mixing in it. So if S is any infinite set, or the natural numbers, or the integers, is any infinite set, then there exists n1 less than n2 less than ... all in S. So I can take an infinite collection of these where I'm taking them without repetition. That's what I mean by taking less than each time. Each one of these is in S and they're not being taken with repetition. It's the important thing. So that n1, comma, n1 plus n2 plus, comma, n1 plus n2 plus n3, hopefully you guys are getting the pattern, is a mixing sequence. What do I mean by a mixing sequence? I mean, for any measurable A and B, the limit as, let's say, K goes to infinity of the measure of A intersect T of B. So I take this to be my mixing sequence and call that my mixing sequence. I can tell you what that is in this case. It's just going to be my sums of my n i's from I equals 1 to k. Okay, so these were the terms in the sequence I considered. These were the partial sums. And so this is what it means to be a mixing sequence. Everybody happy about this? Okay. So hopefully this motivates mild mixing as sort of an interesting property. It has a lot of different equivalent conditions. And I should make two more remarks on this, which is remark one, it is weaker than mixing. There are mild mixing but not strong mixing systems. And it is weaker, it is stronger than weak mixing. Every weak mixing system, every mild mixing system is weak mixing. joins, but not vice versa. So it is between mixing and weak mixing. Does everyone here know what weak mixing? I've sort of kept saying weak mixing over and over again. Does anyone here not know what weak mixing means? Oh, okay. Okay. Thank you for the question. I love weak mixing, so I just feel excited I get to say the definition. So I'll say weak mixing. So Rx is weak mixing if it has no, and I'll keep with the convention of writing the word non-trivial in blue, I guess. Eigenfunctions. That is, if there exists F in L2 of mu and alpha in the unit circle in the complex plane, so that F composed with T is equal to alpha F as L2 functions, then F is a constant function. As an L2 function. Okay, that makes sense. So
For all? Or some,
So non-trivial eigenfunctions. So if I have an eigenfunction, so this is the setting of being an eigenfunction, and this is what makes it a trivial eigenfunction. Thanks for the question. Any other questions on this? So similarly, weak mixing has other conditions like this. So for example, the version of condition 3 that you have is that there exists a subset of the integers of density 1, so that any sequence going to infinity in that is a mixing sequence. This is a stronger property. I think the jargon is, this is an IP star set, the mixing sets. And the product version for weak mixing, which I already said beforehand and should have defined weak mixing before I did that, you drop the possibly infinite measure preserving system. It's just usual finite measure preserving systems. You ask for the product of that with your system to always be ergodic whenever the finite measure preserving guy is. Everyone okay with this?
So there's an analog of higher order mildly mixing.
Yeah, there's a story behind this, and I think both for weak mixing and for mild mixing, the higher order versions are the same, but the statement of what it means is a little complicated to say, and I won't get it right off of the top.
So it's not fine that you just take like in your third equivalent definition.
I don't remember. I don't.
Okay, so it's not interesting to study this.
It is, but I'm not going to be able to do it correctly now.
But there is a natural analog in definition 3, right? But that's not it. They just take the KIs, they take the sums and they take the KIs going to infinity, different KIs going to infinity.
I don't know. I don't want to. I'm not going to answer this question.
Excellent.
Any other questions? All right. So I have now defined minimal self-joinings. I've defined mildly mixing. It's taken me half my talk to do that, so I think I'll just get through all of the definitions, because rank one's a lot harder to define. And even harder to motivate. Okay, so, but hey, that's part of why I wanted to give this talk. All right.
If you cross the rank 1 from your statement, is your theorem still interesting?
I mean, what does interesting mean? I think it was probably known in the 70s. So
Without rank.
without rank 1, yeah. Okay, so definition, So first I'm going to put down a definition that won't be of particularly much help to anybody, just as a warning. So if when you see the definition, you're like, what am I supposed to do with this? Don't worry, I'll try and explain it a little better. Okay. Okay, so X is called rank 1. If there exists a sequence of measurable sets, J1, J2, all subsets of my space I'm in X measurable, N1 less than N2 less than all natural numbers, so that the following two conditions hold. 1, Ji, T of Ji, all the way up to T to the Ni minus 1 of Ji are all disjoint as sets. So I have Ni disjoint sets like this. And then here comes the hard condition, which is for every measurable set, A, okay, and epsilon greater than 0, there exists a K. So the K will be the index on the J and respectively the N. And what I want to do is I now want to pick out a subset of these which approximate A pretty well. So what I'm going to do is I'm going to be looking at the measure of A, and I'm going to take the symmetric difference with something, and I'm going to ask that that's small. Okay, so I want to approximate my A pretty well. Okay, so what this is going to be, this is going to be 0 less than or equal to M1 less than less than MR, which will be less than NK. So this K is the K here, and then these will be images of my J. I'll take unions of images of my JK, and it will be T to the MI of those. I equals 0 up to, nope, I equals 1 up to R. So what I'm saying is I can approximate any measurable set pretty well by these disjoint copies, so long as I've refined my set well enough. So just to kind of hammer home a little bit what's going on here, in a context with no dynamics in it, if you consider the dyadic intervals in the 0 to 1 interval, you can always approximate any measurable set pretty well by finite unions of dyadic intervals. And even with the same denominator, it's not hard to do. Okay? So that's sort of one way of thinking about this. These sets are giving you something that sort of probe your space disjointly quite well.
This kind of means that I can approximate my sets in the sigma algebra by Rockling towers or something.
Yeah. At specific times. Okay. So I think it's worthwhile to contrast this to the so-called Rockland lemma, which works for all time. The Rockland lemma, not so-called, the Rockland lemma. The Rockland lemma works for all times, not a specific sequence. And you get disjoint copies, and the union is almost all of the space. But it's very rare you'd be able to approximate a given set with this. And indeed, the proof of it often goes that these pieces are sort of scattered. Your thing J and the Rockland lemma is made up of a union of a lot of different pieces that are scattered throughout your space. Okay, so this is quite different than the Rockland lemma, though this is sort of a helpful way of thinking about this. It's a much stronger. Okay, any questions on this? Yes.
What's a good example of a rank one system?
Yeah, thank you. So I'll first do the classic thing of examples, which I'll say things I care about and maybe very few other people in the audience do. So let's do some examples. Almost every IET is a rank 1 system. Almost every IET is rank 1.
The village thing?
Yes. And this is Veach. Ergodic rotations of the circle, every ergodic rotation of the circle. The circle, this is Del Honco.
Irrational rotation.
Correct, irrational rotations of the circle. Del Honco. Odometers are another example. Odometers. And this one's pretty straightforward. So who here knows what I mean when I say the word odometers? Not enough people, so let's increase the number of people who know what I mean. So I want to consider a system, and you could imagine I take a product, and for the sequel of the talk, which I might not get to, I'm going to give myself more generality here, and I'll let myself go from 0 out to some c sub I minus 1, say. Okay, so I want to give myself a product of finite point sets, okay? And I want to consider the product of counting measures on this set. And I want to have a map of this space to itself, which is +1 with carrying. So my T on this space, so this will be my space X, and T will map X to itself, which will be +1 with carrying. So let's do the simple example where all Ci are equal to 2. So if all Ci are equal to 2, what I would do is I have T of 1, 1, 0, 1, 0, 1, 1, and so forth. So I want my map to be +1 with carrying. So I add 1 here, and since I want to compute things mod 2, this should go over to being 0. Is everybody okay with that? So this becomes 0. And then I carry my +1 over to here. So this becomes 0. Now I carry my +1 over to here. So this becomes 1. But then I stop doing it. 1, 0, 1, 1. So is it clear what this means by +1 with carrying? And of course, if this had been 1 and maybe C2 was equal to 3, so if this was 3, that would become 0 and then would move over each time. Everybody okay with this? Does anyone want to see a formula of this, or are people okay with this? Great. Okay, so this is another example of a rank 1 system. And I will do one example in a little more detail in a minute, but I want to, maybe actually I will go over to this example. So there's a historically important example of a rank 1 system that perhaps motivated the definition of rank 1 systems. So there was a question in so it's natural in a subject to ask whether different properties are equivalent to each other. That's sort of part of the point of this talk. But one can ask this about mixing properties. So there was a question of whether every weakly mixing system was strongly mixing, whether there was any difference between them. And this was proven by a series of 2 papers which showed that, so you can put a topology on the space of invertible measure preserving systems called the weak topology. And in that topology, being mixing is a rare property, it's a meager property, and being weak mixing is a common property. It's a dense G delta, its complement is a meager set. And so you just intersect these 2 and you get a weakly mixing but not strongly mixing system. And there's a natural then question like, give me one. Okay, this is great. Don't get me wrong. Knowing that it exists is great. But how about give me one? Okay, and my belief is that in the early 60s, Chacon came up with the first one, and it turns out to be what one could call a rank 1 system. And so how is this going to work? So what I'm going to do is I'm going to define my map on larger and larger subsets of my space, and this will give me flexibility to add in additional sets to my space to give me some room to work with in my properties. I don't know if that made sense quite yet, but I'm going to define my map on most of my space, and then at iterative steps, I'm going to define it on more and more of my space. That's how it's going to work. So you could imagine I start off on defining it as 3 sets like this, and I'm just going to have my map go like this. And then when I get here, I don't know what to do. So now I'm going to tell you rank 1 sometimes are called cutting and stacking. So the way I'm going to build these is I'm going to cut them and I'm going to stack them. And this one I'm going to cut into 3 pieces. I'm going to stack the 3 pieces on top of each other. And then I'm going to repeat this procedure. Okay? But I haven't defined it on all of the space. So when I get here, I could do things like adding in some of my space. And that's exactly what I'm going to do. On this last piece, this part here will go to the middle part here. This part here, I'll add a new part of my space to it. Okay? And I did some prep work to give you an example. So this picture is the example I had before. And now what I'm going to do is I'm going to cut it into 3 pieces. And I'm going to stack those 3 pieces on top of each other. So this here is this first third. So first third, first third, first third. Okay? Everybody okay with this? This is the second third. And what I've done is I've taken a little bit extra of my space and added that in, and I've colored it red. Okay? And then the third tower I leave the same. Okay? So I doubt I will get this far in my talk, but just in case I do, you can call these objects towers. And you can call these individual pieces levels. And you could call this stage 1, or let's call it scale 1. This could be called scale 2. Are you okay with how this works? So now I'm going to repeat one more time. I'm going to cut it into 3 pieces. And then I'm going to stack them on top of each other. And I'm going to have gotten to the lecture room extra early to do that. And so this is the picture. And I've kept with the colors. So what you see as blue came from the original level of blue. What you see as red came from the original level of red. And orange is the new color. Okay, everybody happy about this? I hope this captures it. So what are my JIs in this setting? They're going to be the first level in each of the steps. So this is going to be J1. This is going to be J2. This is going to be J3. And clearly its images travel disjointly by construction. It winds through here, it comes down, it winds up through here, winds through here. Hopefully it's pretty believable that these disjoint images behave a lot from the point of view of just measure theory without dynamics, like the dyadic rationals up to some diameter. They give a pretty fine mesh describing my space. And so I should be able to obtain a property like this one. Okay. Did that make some level of sense to people? Okay. All right. So let's say a few words about why we care. So why we care.
Question, what is a concrete example of a non-rank 1 system?
Presumably the Horus cycle flow? Definitely the Horus cycle flow.
Bernoulli shift.
Bernoulli shift. These always have entropy 0. That's one property. But there's tons of entropy 0 with things like the Horus cycle flow or the time 1 map of the Horus cycle flow that do not have this property. Okay. All right, so why do we care? So one reason why we care is the typical measure preserving system. In the weak topology. Is rank 1.
You said zero entropy, but it could be any growth rate, right? It doesn't have to be small growth rate.
I don't know. I believe that, but I don't know. Yeah.
Can you explain, like, what am I supposed to be thinking of when I see the word rank in this definition?
Yeah. So the word rank is used a lot of ways in math, and I use it in my own research in different ways. So if I talk about rank 1, I might not be talking about this. I'm stuck with the language. So, but in any case, why on earth would you call something rank 1 if there's not other notions? So you could imagine I could play a game where I still want this property, but I don't just want them all to be images of one interval. I want to allow myself maybe 3 different intervals, 3 different times comparing to them, so that they travel disjointly and I eat up most of the space with those. And I then get this approximation. That would be a rank 3 system. Did that answer your question? Great question.
How much worse are those, so to speak, in terms of why are you sticking to rank 1?
I think this answer to your question had already been known. So the typical is rank 1. So one reason to think about this is if you want to use a bare category argument on measure preserving systems, ask yourself first if it obviously false for rank 1 systems. And if it is, maybe don't try a bare category argument. Also, it's natural you have a notion of typicality, ask what those things look like. Might be another reason. So another reason to think that they're interesting is that a lot of explicit systems that some of us may care about, maybe only the guy at the chalkboard, but at least one person here cares about, falls into it. So it's a more general class that covers some of the examples that I know and love. Okay? And then another reason is that they have a bit of their own theory. So not only are they in some sense typical, but they have some theorems that talk about them. They have sort of their own theory. Okay, and let's give some examples of this. So they have simple spectrum. Okay. And then a question that one can ask is their spectrum always singular with respect to Lebesgue? So question, always singular with respect to Lebesgue? I need to put a question mark here. The centralizer is the weak closures of the powers. Powers. And so a natural question, this is a theorem of Jonathan King.
I don't know. He was in graduate school.
Oh, cool. So question is, what about joints? So this to me is one of the most exciting questions about rank 1 systems. Are all of the ergodic self-joinings, say twofold self-joinings of a rank 1 system, weak star limits of joinings of this form, or these off-diagonal joinings that I talked about at the very beginning? This is open. I think it's a wonderful question. It's also a question of Jonathan King. He asked it. Okay, so factors are always rigid. So factors of rank 1, they have very restricted factors of rank 1. Are rigid systems. So that means systems for which for which there's a sequence of powers so that you converge to the identity in this weak topology. Equivalently, that your Koopman operator converges to the identity in the strong operator topology. So the factors are quite restricted. This is also a theorem of Jonathan King. Mixing implies mixing of all orders. All orders.
Oh, that's normal.
Calico.
Yep, this is Calico.
Taught me. So you're taking me back to my.
And I should mention that the word finite, we asked about other ranks, rank 2, rank 3, so forth. This was generalized by Rijikov to finite rank. Rijikov. Get my spelling right. To finite rank. And then this also has a question. What about, are all PID joinings, are all pairwise independent joinings? So I haven't actually read Kalikov's proof, but Rizhikov's proof, what he proves is he proves that for mixing finite rank systems, if you consider a joining like this, where that's a weak star limit of these, where the projection onto each coordinate is product, then it has to be a product measure. So pairwise independent implies product, but he really uses that they're mixing. He doesn't just, he uses that they're finite rank and mixing. So what he doesn't do is he doesn't show that finite rank or rank 1 systems that have pairwise independent joinings have product joinings. He does this under the assumption that they're mixing. Okay. Are people okay with this? So this still leaves open this question of joinings of products. And maybe I will motivate my talk a little bit about talking about this in connection to the talk. So you could ask, what type of rank 1 systems might have pairwise independent joinings that are not products? So what could this example look like? Could a rank 1 system with a pairwise independent joining is not a product. Look like. Okay, one, it can't be mixing. That's Rizhikov. Rizhikov. Two, it can't be rigid. So why is this? It would have the spectral measure, so spectral type would be singular with respect to Lebesgue. Singular. And Host says PID implies product.
Actually, I'm confused. What King proved factors of rank 1 are rigid, but
Yes.
But you said that the rank one could be mixing.
Yep. So maybe I can say another word. Rank one systems that are mixing automatically have minimal self-joinings. So, fact, also due to King, mixing rank ones. Have minimal self-joinings. Okay, so thanks for the question, Alona. It's a very helpful question. So rank ones really have a little bit of their own theory. And in that theory, there's a lot of overlap between mild mixing and mixing. So this talk has a couple of motivations for it, but one of them is to differentiate the class of mild mixing from mixing rank one systems. So in particular, mixing rank ones and mild mixing rank ones are automatically prime, meaning they have no interesting examples like this. And that's because they can't have rigid factors. Because mild mixing just means no rigid factors, and mixing also means no rigid factors. It's not the only thing mixing means, whereas for mild mixing, that's the only thing it means. That's the definition. So both of these are automatically prime. Okay? Minimal self-joinings, when you're weak mixing, you're also prime. So you could ask, did that go through as well? And the point of today's talk is that it didn't. Did that answer your question?
Yeah.
Mixing rank ones have MSG. Okay, so it can't be rigid. Okay, so now we have the third possibility. And if the answer of Thouvenot's question was negative, so if there was a negative answer to Thouvenot's question, which there isn't, if there was a negative answer to Thouvenot's question, this would solve the problem. This would solve the problem. All right. And this requires a little bit of explanation. So minimal self-joinings implies a property called being too simple.
Sorry.
Okay, there were several questions Thouvenot mentioned.
Oh, yeah. Oh, sorry. Does there exist is every mildly mixing rank one have minimal self-joinings? So the point of today's talk is that the answer to his question was negative. And if there was a positive answer, thank you, Lord. Positive. So if there was always minimal self-joinings, then, yeah. Did that answer your question?
Then what? You answer what question? There's so many questions.
This would solve the problem.
What problem?
Oh, the problem of whether all pairwise independent joining implies product in the class of rank one systems. Thank you very much. Sorry, I didn't understand. Thanks for, yeah. Other questions? Great. Who's with me at this point? Should I take a step back? Okay, great. Thank you. Okay, great. So minimal self-joinings implies a property called too simple, and then too simple plus weak mixing. Too simple plus weak mixing implies and pairwise independent join not product implies should do a bigger arrow here, implies factor with Lebesgue spectrum. But if you're mildly mixing in rank one, you can't possibly have a factor with Lebesgue spectrum because you can't have any factor, let alone with one with Lebesgue spectrum. And so I should give names here. This is Glasner, Post, and Rudolph. All together. but I'm just writing it in this way so that it happens. So we would have known if the theorem wasn't true and the opposite was true, we would know that for rank 1 systems, pairwise independent joinings implies product. And I think this is a good place to stop. Thanks.
Is your example human?
It is explicit.
Doesn't fit into any of these. Just both as a book.
Yeah, so unfortunately, the bookkeeping is a serious issue. And so I do something I work the opposite way that these work. So what I start with is an odometer with what me and Donald do is we start with an odometer with a variable base, and we build a rank 1 system as a first return map to a more or less explicit subset of this. And then we prove that that has an interesting joining and that it's mildly mixing. Did that answer your question a little bit?
Yeah, it's rank 1.
And is rank 1. Yes, it's not obvious that it's rank 1, though it's not. That part is the easiest.
And the self-joining is coming from where?
Yeah, so if would take me 5 minutes to answer that question. Can I answer that after the talk? I have an explicit way of building self-joinings that I did in prior work with Alex Eskin and Brian Craw. And we need to develop that a bit.
How many self-joinings is there?
So our example only has a 2-to-1 self-joining. So that means you've got a self-joining, so it's the system with itself and it's got a measure on the product system. You can consider the projection to each coordinate and you can ask about disintegration of measures. And you can then ask, what do these measures look like? So in our situation, these measures are atomic measures and they're supported on 2 points on each fiber. I think that with extra work, you might be able to build more complicated things.
You know
but
all the
it would be-
self-joinings? You know all the self-joinings?
No, not in this example. I just produced them. But I think you could build ones that have kind of richer self-joinings, but I think that would be, it sounds technically challenging to me.
You were saying something about approximating these self-joinings by the diagonal.
Yeah.
So in this example, is that possible?
Yes, it is. In this example, there is an explicit sequence of powers where you converge to this. And that's sort of how this construction of joinings works. That goes back to my work with Alex and Brian.
You have a paper with Alex and Brian?
No, separate papers, sorry. A paper with Alex and a paper with Brian, sorry.
Any more questions? If not, thanks all again.